Today we're going to talk about the binomial probability distribution and binomial probability experiments. A binomial experiment is a statistical experiment that has the following properties. 1. The experiment consists of n repeated trials. 2. Each trial can result in just 2 possible outcomes. We call one of these outcomes a success and the other a failure. The probability of success, denoted by lowercase p, is the same on every trial, and the trials are independent. That is, the outcome on one trial does not affect the outcome on other trials. We define the particular binomial experiment as follows. We use the parameter n to represent the number of trials of the experiment. We use lowercase p to represent the probability of success in one trial of each time we do the experiment. Q is always equal to 1 minus p. For the rest of everything we do in statistics, a Q is always 1 minus p, and it represents the probability of failure for one trial of the experiment. And X represents the random variable that represents the number of successes under consideration for the problem. But note that there can be more than one X for each problem. I'll explain this as I go through the problem that we're going to work on. So, as I already said, we define the at least parameters for the particular binomial experiment as follows, but then we also have something called the mean or expected value or expectation of the experiment, and that we just take n, which is the number of trials, times p, which is the probability of success for each trial. Now that only works for what we call binomial experiments. The variance is simply n times p times q, and the standard deviation is the square root of the variance, which is the square root of n times p times q. The probability of X successes in a total of n trials is the probability of X equals the number of combinations of n things taken X at a time times p raised to the X power. That means the probability of success in one trial raised to the X power, and then Q raised to the n minus X power. That is a long, complicated formula. And of course, we're going to use spreadsheets to take care of all of that. But this is the formula for it, and back in the day, we would have to plug all those things into a calculator for each thing that we're supposed to do. A recent survey asked Republican voters whether or not they were concerned about climate change. The results concluded that 47% of Republican voters seemed to be concerned about climate change. If 12 Republican voters are randomly selected, determine the expected number of those that are concerned about climate change. Well, the expected value is simply n times p, and we'll get to that on a spreadsheet. The variance of those that are concerned about climate change, and we can calculate A, B, and C very easily on a spreadsheet, so we'll come back to those. Let's look at D. The probability that 4 are concerned about climate change. That means 4 out of this 12 over here. Part D, what N, P, Q, and X are. N is the total number of trials. So the way I have this worded, N, for all of the problems for A through F, will be 12. P, as I said, is the probability of success on each trial. The experiment is randomly selecting a Republican voter. And each time I do that, there's a 47% chance that that person would be concerned about climate change. We don't write these things as percents, we write them as decimals. I hope you can easily convert 47% to 0.47. So for part D, N is 12, P is 0.47, Q is 1 minus P, and that would be, in this case, 0.53, because 1 minus 0.47 is 0.53. Now, X, that's the thing for this problem that will throw students off. For part D, we're wondering what the probability that 4 of those people who are selected, 4 out of the 12, will be concerned about climate change. So in this case, X is equal to 4. Now when we say the probability that 4 are concerned, we mean exactly 4. Not 4 or more, not 4 or less. We mean exactly 4. So for part D, N is 12, P is 0.47, Q is 0.53, X is 4. Let's take a look at part E. The probability that at most 5 are concerned about climate change. What that means is N is still 12 for this particular problem. P is still 0.47. Q will still be 0.53. X is going to be 0, 1, 2, 3, 4, and 5. Because at most 5 means no more than 5, but it could be 0, it could be 1, it could be 2, it could be 3, it could be 4, it could be 5. Let's look at part F. F asks about the probability that at least 7 are concerned about climate change. That's 7 out of 12, and it's at least 7. That means the least amount could be 7, which means 7 or more. So that would be either 7 would be concerned, or 8, or 9, or 10, or 11, or 12. Now you can't go more than 12 because we're only selecting 12 people for this particular problem. Also, we can't go below 0 because that would be meaningless. Let's head over to spreadsheet mode and see how we solve each of these. Here we are in spreadsheet mode. Let me remind you what the problem we're trying to figure out is. There are Republican voters. We randomly select 12. We know that each selection has a 0.47 probability of that person being concerned about climate change. So let's go to our parameters. First parameter is N, and that tells me how many times I'm trying the experiment. Since the experiment is randomly selecting a Republican voter, and we're running that experiment 12 times, N is 12. Now, according to the problem, each time we select a person, there's a 0.47 probability that that person is concerned about climate change. So that's 0.47. We don't have to put in Q because in a spreadsheet it will automatically calculate that for you. You just type it in as 1 minus whatever is in the cell B7. Also, the mean, the variance, and the standard deviation are all just simple calculator things, but, why not have it on the spreadsheet? So the mean is simply n times p, so we just type in equals whatever is in cell B6 times whatever is in cell B7. In other words, just n times p. For the variance, it's a similar thing, except it's n times p times q. And I kind of did a little cheating shortcut here. Since the mean is n times p, we already have the n times p part, so all I did was take whatever the mean is, and then I multiplied it by whatever q ended up being. And now the standard deviation is just the square root of the variance. And we typed in equals. The function for square root is SQRT. And then we take the SQRT of whatever is in cell B11. And there we have it. Now, we're going to talk about binomial probabilities, and the random variable x, that's what we call this column, the random variable. I already stated that we can start off as low as 0 and work our way up as high as 12, but no more than 12. Again, if we're only selecting 12, we can't get 13 or 14 or 15 people that care about the environment, or global warming in this case. And we can't get less than 0 because that would be meaningless. So I'm going to just type in a 0 for the first cell. You can simply just number the next cell down as 1 and then 2 and 3. But we have a little bit easier way of doing that. Instead of doing it that way, we can use a function to keep adding to the next cell. And the way I do that is after I type in the 0, I'll type in equals. I click on the cell right above, which is cell D4. And then I say plus 1. And now I'm going to click back on that cell and drag and drop that all the way down to until I see a 12. Whoops, I only went as far as 10. So let's go a couple further, and there we have it. So now we have all the possible outcomes that can occur. There can either be 0 out of the 12 on up to 12 out of the 12. It would be extremely unlikely that all 12 would be concerned about the environment given these parameters, and it would be also not so likely that 0 would be concerned. In fact, we can estimate how many will be concerned by taking a look at the mean. And this is what I meant when I said the mean is also called the expected value or the expectation. We would expect about 5.64 of these people to be concerned about climate change. Now, we can't have 5.64 people, So the most likely occurring thing would be somewhere between 5 and 6 people. It would be the most likely occurrence. Now, that doesn't mean that it'll be 90% or anything in a case like this. It's just going to be more likely than any of the others. I gave you a really long formula when we were going through the actual problem on how we calculate binomial probabilities. Now, I'm going to go through this using that long formula at first. So don't copy what I'm about to do yet. We're going to truly take advantage of the spreadsheet at some point, but just don't do what I'm doing at first. So let's go back to the problem and the formula. And here we have it. The probability of X successes in N trials is, and then we have P of X equals the number of combinations of N things taken X at a time, the probability of success in one trial raised to the X power, and then Q raised to the N minus X power. That's a pretty long formula, and I'm going to type it in the long way, and we will take it from there. So this is going to equal. We have a combination formula in the spreadsheet. Combine N things. So I'm going to click on this N, and when I do that, I have to decide, do I want that cell reference to be static or dynamic? In this case, it's static because for this problem, it's going to always be 12. Keep in mind, other problems, it will be different things. So I'm going to simply type a $sign before each one. I already went over what that means. It's a static cell reference. I don't want it to change. And then comma, the number chosen comes from the random variable. So for this particular cell, I want it to be 0. I'm going to close my parenthesis and say times, I'm going to open a parenthesis, and then we're going to take P, which is in cell B7. Then I have to decide, do I want that to be a static reference or a dynamic reference? And we always want that one to be a static reference. So I'm going to put the $sign before that. I am going to raise that to the X power. I'm going to close my parenthesis, times, which remember is Shift 8, open parenthesis, Q. I want that to be a static cell reference. Yes, this is long, so I put the $signs before that. And I am going to raise that to the, again, this is complicated, N as a static cell reference minus X, which is a dynamic cell reference. I'm going to close a parenthesis for the exponent, the Q raised to a power, and press enter. And there we have that number, which is a pretty small number. It's 0.00049, etc. Now I'm going to drag and drop all that down, and there we have it. If you look at the probabilities, this means the probability that out of all the 12 selected, that 0 of them are concerned about climate change. This number represents that exactly one of them is concerned about climate change. Now, if I look at 5 and 6 in particular, look at the probability there and compare it to all the other probabilities. All the other probabilities are less than whatever the probability of 6 is. Again, going back to the mean, that is the expected value, or the number of people about that we would expect who would be concerned about climate change if I selected 12 Republican voters. I'm going to get rid of all of these, and I'm going to do this by taking full advantage of a spreadsheet using a spreadsheet function. We have a spreadsheet function that takes care of all of this for us. However, we still have to be concerned about static cells and dynamic cells. I'm going to type in equals, and since this is binomial distribution, I'm going to start out with BINO. And if you see, we have binom.dist. Okay? So I'm going to double click on binom.dist. The first parameter that it wants is the number of successes about which I am concerned. That comes from X, my random variable right here. And do I want that to be static or dynamic? That's right, I want it to be dynamic. I want it to change so I don't put the dollar signs before it. Now, press comma. It's asking for the number of trials. That means N, and always represents a number of things. And for the binomial distribution, it's always the number of trials. You click on that. Now, do I want that to be static or dynamic? That's right, I want that to be static, so I am going to put the dollar signs before each one of those things. Comma. Now I want to click on the probability of success for each trial, in other words, lowercase p. I'm going to click on that, and do I want that cell reference to be static or dynamic? The answer is static also. I don't want it to update as I drag and drop down. For this problem, it's always 0.47. So I'm going to put the dollar signs before that, comma. And now it's asking whether or not I want this to be cumulative. For this column, the answer to that is no or false. One cool thing about spreadsheets is that the number 1 represents true and the number 0 represents false. So in this case, I don't want it to be cumulative, or I want it to be false that it is cumulative. So I'm going to click on that. Or you could type in the word false, or you can just type in the number 0. No matter what you do there, it still should work out to be correct. I'm going to close my parentheses and press enter. And you'll see we came up with the same number as what we did when I did it with the whole long formula. So this is the way you're supposed to do it. It's binom.dist, open parenthesis. We have D4, which is taken from my random variable X, and then comma N for the number of trials, and that's in cell B6. Again, that's a static reference, comma P, which comes from cell B7, and that also is static. And for this column, I don't want it to be cumulative. Now that I have that, I will drag and drop the whole thing down. And the numbers are exactly the same as they were before when I did it by the long formula. Now, because this is considered to be a probability distribution, I know that the sum of all the probabilities, the sum of all the possible things that could happen, has to equal 1. So I'm just going to verify that right now, and then I'm going to delete it. But I just want to, well, prove a point to you. This will equal the sum of everything from here to here. You don't have to do this. This is just so that I can show you how this all works out. And as you can see, when I added up everything here, the sum was 1. So the sum of all the probabilities is 1. This helps us to answer one of the questions. Question D asks, what is the probability that 4 are concerned about climate change out of the original 12 that I selected? All we have to do now is look right here, and my answer is roughly 0.1504. So that answers question D. Let's take a look at question E. Part E of this question wants to know the probability that at most 5 are concerned about climate change. So what does that mean? When we say at most 5, the meaning of that is that either 0 or 1 or 2, 3, 4, or 5 are concerned about climate change. So basically, the sum of all of those values would be how we determine the probability that at most 5 are concerned about climate change. Let's go to spreadsheet mode. Here we are in spreadsheet mode, and we have either 0, 1, 2, 3, 4, or 5. These are the probabilities that exactly this number of people are concerned about climate change. Meaning, if I wanted to know the probability that exactly 3 people were concerned about climate change, the probability would be 0.0753 and so on. And we already discussed the probability that 4 people would be concerned about climate change. That's 0.15038, etc. This would be the probability that none of them, out of all 12 of the people that we pick, this is the probability that none of them are concerned about climate change. That's a pretty small number. That's 0.0004. So that's 49. So roughly 0.0005 or 5/10,000ths probability. Well, if I want to know the probability that at most 5, as I've already stated, that's a probability that either 0 or 1 or 2 or 3 or 4 or 5 people are concerned about climate change. We can simply just add all of those up. For example, I can just type in, now don't do this, we have another way of doing it, but for right now, we can say equals sum, open parenthesis, grab the one at 0, go all the way to 5, close parenthesis, press enter. And my answer would be 0.4703 and so on. And that would be the probability that at most 5. If we look up here, this says the probability that x is less than or equal to some big X. That's just the algebraic way of saying that. In other words, that x, my random variable, is less than or equal to, in this particular case, 5. I'm going to delete this that I just put. And I'm going to show you how we actually do this. Now, before I do that, if I said the probability of at most 0 or exactly 0, it's really just the same thing. At most 0, well, there are no numbers in this sort of discrete distribution that would be below 0. You can't have negative one person. Well, in the real world, you can't have negative one person be concerned about climate change. So let me just get right to it. I'm going to type in equals and bin, and we're going to go back to the binomial dist function, just like we used before. It's the exact same one. And again, it's asking for the number of successes. Well, that would come from my random variable column. So in this particular one, the number of successes would be 0. And I want that to update as I drag and drop down. I know this seems exactly the same thing as what we did in this column here, but there is one difference. So I'm going to press comma. And now the number of trials, well, that comes from this cell right here. And I always want it to come from that cell. So I'm going to put the dollar signs because that's a static cell reference. So I put the dollar sign before the B and before the 6. And then comma. And we want to know the probability of success in each trial. So I would click on this cell right here. That's the probability of success on each trial. And do I want that to be static? Yes, because I always want it to come from this cell right here. So I'm going to put the dollar sign before the B and before the 7. And then now comma. And now it's asking me if I want it to be cumulative, just like before. Just like this column right here. But when I did it here, I put false. Cumulative means the same thing as accumulate. In other words, when I say true, yes, I want the values to accumulate up to and including that value. So this time I'm going to type in or just press on true. Then I'm going to close parenthesis. As I told you before, this cell right here and this cell will be the same thing, because if I said at most 0 people are concerned about climate change, or exactly 0 people are concerned about climate change, it means the same thing. So let me go back here, and then I'm going to drag and drop that down. And as you can see, it basically adds up this cell plus the one that comes before it, or this particular cell. We'll take all 3 of these, add them up to get you to this, etc. And before, when I said at most 5 and I showed you the sum, it worked out to be exactly this number. So again, for the probability at most, we would use the last parameter we would set to be as true. If we look all the way down here, we end up with 1. Now, does that make sense? And the answer to that should be yes. That absolutely makes sense. Why does that make sense? Well, it makes sense because we have 12 people. We selected a total of 12 people, and the probability that at most 12 say they're concerned about climate change, well, yeah, that's a probability of 1, because it's either going to be 0 people, or 1, or 2, or 3, all the way up to 12. So, yeah, that's going to be a pretty solid probability. I would bet on that. Let's look at part F. Now, for part F, it says the probability that at least 7 are concerned about climate change. Again, let's think about what that means. At least 7 means 7 or more, or 7, 8, 9, 10, 11, or 12 people would be concerned about climate change. And for this particular problem, we can't go above that 12 because we've only selected 12 Republican voters. So it wouldn't make sense to say that 13 of them were concerned about climate change. So again, for this particular problem, since we're only conducting 12 trials of this experiment, of this binomial experiment, it only makes sense that we can go up to 12. Let's go to spreadsheet mode. Okay, so just like before, I can add them up. Like, for example, if I want to know the probability that at least 7 are concerned about climate change, I can take this cell, add it to this one, this one, this one, this one, and so on. And that would make perfect sense. However, we do have another way of doing that. And that is using what we call in probability and statistics the method of the complements. So the complement of at least 7, meaning 7 or more, complement sort of means the opposite of. It would be 6 or less. So the complement of 7 or more would be 6 or fewer. And quite simply, this number right here gives me 6 or fewer. In other words, it says at most x over here, x is equal to 6. So this would give me 6 or fewer. So since the sum of all the probabilities, remember, for all probability distributions, the sum of the probabilities is always going to be 1. This cell right here, I can say just equals 1 minus, and then I'm going to go to the complement, which is represented just by this cell right here. Then I'm going to press enter. And that would give me the probability that at least 7, meaning 7 or more people are concerned about climate change. Okay, I'm going to grab this right here just to fill in the rest of this. And you'll see that as we go down here, this number gets smaller and smaller, meaning here it's roughly 31%, roughly 14%. Probability of 9 or more is roughly 5% or 0.048, whatever. We could actually also drag and drop up here. So I'm going to do that. And yeah, it gives me a little bit of an error message for this first one. I can tell you that for that first one, it's simply just going to be 1. It's the exact opposite of, well, not the exact opposite, but this right here almost means the same thing as this. In other words, if I said, what's the probability that at least 0 people out of the 12 people, so at least 0 out of the 12 say they're concerned about climate change, well, the probability of that is pretty good because, at least 0 of them will say they're concerned about it. And then from there, the numbers simply go down. So I just manually typed in a 1 right here. The question sort of wouldn't make sense if I said, what's the probability that at least 0 say they're concerned about climate change? If I said, what's the probability that at least 1 out of all 12 of the people are concerned about climate change, that's actually pretty close to 1. This right here would mean, what's the probability that at least 11 are concerned about climate change? So that would mean either 11 or 12 people are concerned about climate change. Well, here you have a table of binomial probabilities. And this table is actually set up to work for any binomial distribution type problem that you have. You just might need to extend things a little bit further. For example, you might get a problem where there's 16 trials, so I'm going to type in 16. Okay. The probability of each trial is, we'll say 22%, so 0.22. Q will automatically update. It'll automatically update the mean, the variance, and the standard deviation. And the issue with this is that if you notice here, I only go up to 12. I need to go further than that, so I need to go up to 16. Let's see. And there we go. I went up to 16. And then I would need to drag and drop all of these down over here. And let me explain to you what those little E's mean over there. Okay, so this E, this one right here, it means 7.36894, and E means times 10 to the negative fifth. So it means 0.00007368994. Pretty small number. So as this number after E with the minus sign gets larger, this number actually gets smaller and smaller. This means 3.011 times 10 to the negative 11th power. Basically, that's going to be 0.0, and then you're going to end up with 10 zeros and then a 3. It's a very small number. If you ever get numbers like that and you're asked to find the probability and you have something like times 10 to the negative 8th power, essentially you would just type in the number 0, because we're not going to ask you to round at the 100,000th place or beyond. At least usually we don't. Okay, so just keep that in mind, that if you change n, you would have to update all your column information as well. So that's it. That's our lecture on binomial probabilities and binomial probability distribution. And I hope this lesson helped.